Good evening and a very warm welcome to 16th lecture of IPA50 series, New Horizons in Physics. Today we bring another exciting talk to you, which is given by Professor Shikha Varma, and she's going to take you from the world of surfaces to nanotechnology to nanobio. To introduce today's speaker, we have Dr. Shalik Joshi, who actually is a former student of Professor Shikha Varma. He also worked as a scientist in Tata Steel R&D, and now he is currently at Ulsan National Institute of Science and Technology doing his postdoctoral fellow. So clearly is the area which is forms a boundary of the physics, applied physics and the industry. So we look forward to a lot of exciting things from today's talk. And I now invite Dr. Shalik to introduce today's speaker. Over to you, Dr. Shalik.
Thank you, ma'am. First of all, let me take this opportunity to congratulate Indian Physics Association for completing 50 years.
Can you be a little loud?
Oh, okay. Sorry. So, first of all, let me take this opportunity to congratulate Indian Physics Association for completing 50 years and celebrating this in a very unique way, which I strongly believe will help a lot of young minds who have just entered in research. And I'm extremely grateful to Indian Physics Association also for giving me an opportunity to introduce Professor Shikha Varma, with whom I pursue my PhD. I really feel grateful about that. So, actually, Shikha Varma is a professor at present in Institute of Physics, Bhubaneswar, India, since 1994. So she received her MSc in Physics from IIT Kanpur in 1984 and her PhD in Experimental Condensed Matter Physics from Syracuse University, New York in 1990. So her research areas mainly includes electronic interaction, electronic structure of surfaces and interfaces, nanostructures and their interactions, and also she focused on nanobio and ion beam interactions. She was also a postdoctoral fellow during 1991 at Case Western Reserve University, Cleveland, USA, and from 91 to 93 in University of Wisconsin, Milwaukee. She was also a visiting fellow during the same period, 93-94, at University of California, Santa Barbara, prior joining Institute of Physics. And she has also published over 140 research articles in international peer-reviewed journals. And she's also currently a member of the editorial board of Journal of Physics Condensed Matter, IOP, publishing from Bristol, UK. Apart from research, she has also been actively involved in several outreach activities hosted by the Institute or several other organizations. And so with this note, I would like to invite Professor Shikha Varma to resume her talk. Start her talk.
Are you able to see the talk, Shalik?
Not yet.
No,
Okay, okay.
To share the screen.
Just let me know when you're able to.
Yeah, you can share the screen now. Yeah.
You are able to see now?
Yes. Yeah, now.
You have to hide we're seeing this presenter's view.
No, I think. Is this the correct screen?
Yes, now it's correct. Now it's correct.
I am not sure. Okay, you are able to.
Now it's fine, and the pointer is also visible.
Yeah.
Just a moment.
Yeah.
Just. Yeah, something has not. Okay, let me just continue. So thank you, Shalik, for a very nice introduction. And on the onset, I would like to again say thanks to Vandana for giving me this opportunity. It's a real honor to be giving talk in this series. And also congratulations to you and other all IPA dignitaries on this occasion of IPA completing 50th anniversary. So The title of my talk is this From Surfaces to Nanotechnology to Nanobio. And I like to give some flavor of this field. It's a very vast field. So the early signs of nanotechnology are there, and it is an old technology, although it was not clear that these stained glasses in Europe churches, these are very famous things that we see. These actually have various nanoparticles embedded in these glasses, although it was not clear how it is happening. But now we know it is there, although the glass makers were doing some recipes, following some recipes which created it, and they didn't know what is happening. But various sizes and shapes can produce variety of colors.
Shikha, we lost you. It's kind of frozen.
Then of the metals, and then going to the semiconductors, invention of variety of techniques. Hello?
Yeah, I think there's some problem. Your screen has also got...
Was there a disconnection?
Yes, looks like that a bit. Can you go back to the screen share?
Are you able to see my screen now?
Yes, but it's not in the slideshow mode.
Now?
Yeah, now it's in the slideshow.
Okay, okay.
Yes, please continue.
Okay, so various phenomena like absorption, growth, scattering of scattering dynamics can be studied and have been studied. And so the fields have evolved through various generations. And I think at present, numerous studies are going on, as will come in the next slide. But primarily it is in these have numerous applications in the field of nanoscience, biological, and clean energy. And if we even concentrate on something like these two techniques, starting from 1950, various generation of achievements have taken place. Many scientific disciplines are involved, going all the way from physics, chemistry, material science to something like biology, medicine. And similarly, there are many technological drivers also going all the way, starting from transistors and then moving on to quantum dots and nanomechanics. So this vast field is very difficult to assess, but numerous applications are coming out of it, these fields every day, which is driving the technology. So surfaces are important because they control many properties of a material, and there are atomic arrangements on the surface, and depending on the atomic arrangements, the properties will change. One can create nanostructures and nanostructures and study the interaction of surfaces with atoms, molecules, biomolecules. And these all together, they show many exceptional and advanced properties. And some of the properties can be in the field of photoabsorption, photocatalysis, sensors, IV characteristics, conducting properties, resistivity properties, catalytic properties. These are some of the applications which have extreme technological importance in our everyday life. So the fabrication of such surfaces or nanostructures can be gained through variety of methods. This is not even a complete list, but some of the techniques that are present are ion beam related, focused ion beam, electron beam lithography in top-down approach, or in bottom-up approach, where you start atom by atom building nanostructures or surfaces. And these are the various techniques. Some of the techniques which I will discuss are a very limited field, is something related to ion beam techniques and something related to the assembly using the DNA or biological synthesis. So these are some of the facilities which are there in IOP. For example, molecular beam epitaxy or DCRF, photolithography, pulse laser beam. And these both all can be used for bottom-up and top-down approaches in making surfaces and nanostructures. So what we will discuss are some of the examples related to some functional surfaces and nanomaterials. So this is the outline of the talk, where first I will just present some results from ion beam irradiation and formation of TiO2 nanostructures. And then we'll go to the nanobio section where we'll discuss some of the how DNA can be used to make nanomaterials. And some applications on the way we'll discuss, for example, photoabsorption and resistive switching phenomena, which is presented by these nanostructures, and some sensing applications and some interaction for biocompatibility in the nanobio section. So starting from the ion irradiation of for the formation of TiO2 nanostructures. So TiO2 became a very important material, and once it was known that it can produce hydrogen in absence of any external voltage. So when TiO2 is used to, the light strikes on TiO2, and this is UV light, in the photochemical cell, with these equations, one produces oxygen at the TiO2 electrode and hydrogen at the platinum electrode. And this production of hydrogen can be used for the hydrogen fuel cell. So this was considered a very major breakthrough, and these are the Fukushima and Honda are, achieved this photocatalysis of the splitting of water. So with this, TiO2 shows exceptional properties, something like it's a very stable compound, high catalytic activity, it's non-toxic, many optoelectronic properties. There are surface states on TiO2 which show special role, and as we go along, we'll see this. And it is also useful in solar cell, chemical sensor, photochemical cell, electronic devices. This is also a very biocompatible material, as we'll see with the interaction with DNA. So these are the two main phases of TiO2, which are usually seen in the film growth or surface modification nanostructures. This is a rutile phase, which has a band gap of about 3 eV, and this is an anatase phase. In both the cases, if you notice that the band gap is of the order of 3 eV, which tells us that it is the UV range which is used to excite electrons. So for example, from valence band to conduction band, if we want electron excitation and using of electron hole pair, then we need to have UV light. And the idea is we want to keep this electron and hole as much far separated so as to use this electron for application. So we don't want this electron and hole to recombine. So these are the main things that we want to achieve. So one thing is that the light driving this valence band to conduction band excitation is UV light, and it will be better for photocatalytic applications if these band gap can be reduced a little bit to use visible light photocatalysis or visible light application. And secondly is that we want to reduce this electron hole pair to come together. We want to keep them separated out so as to use them. So this is what we want, that UV light has a very small spectrum of only 4% in the incoming solar radiation. So visible light photocatalysis, what we want is visible light. So reduction in band gap of TiO2 is one of the major things one wants to achieve. And secondly is we want to reduce this recombination, which is at present less than 30 picosecond, and so its efficiency is low. So one of the ways to achieve this is by making nanostructures in both band gap tailoring and reducing the recombination. So why nano TiO2? So again, it has high surface to volume ratio. Morphology can be changed, which can enhance the light absorption, visible light absorption. And then there are presence of surface states, and one can also control recombination on nano TiO2. So these are the various planes of TiO2. It can be crystallographic planes. For ion irradiation, what we have used is a TiO2 110 surface, and we have used a rutile phase, and we bombard them with ions. The ions what we have used is argon ions. And so this is a top-down approach. The ions come from the top and keep modifying the surfaces. And what we produce are the nanostructures on the surface. For example, what we see is something like this. So in this case, we have used, this is a clean TiO2 surface. But as we start bombarding it, depending on the fluence, we can generate variety of patterns on these surfaces. Only thing getting changed here is the ion fluence. And so this is a single step process for the formation of nanostructures. So how do we produce these nanostructures? What ion irradiation does, it can create vacancies as well as on the surface. And as we go down, we'll see that what we are creating is oxygen vacancies. And also diffusion of atoms takes place when ionization is taking place. The nanostructures are generated due to competition between the roughening, which is caused by the creation of vacancies, and smoothing process, which is caused by the diffusion of these atoms on the surface. These are all non-linear processes, and so there is an instability on the surface, and sputtering yield is a curvature dependent. So the points which are low become lower, and the points which are high on the surface become higher. So sputtering is preferentially more of lighter atoms. And in the case of TiO2, there's a preferential sputtering of oxygen atom, and one produces oxygen vacancies. So how does one see these oxygen vacancies? So for that, we use a technique which is called XPS. In the case of XPS, X-rays bombard the surface and photoelectrons are generated. All this process happens in UHV. This is a only very simple picture. And it happens in ultra high vacuum. You need vacuum to get these electrons and measure their kinetic energy. And then with this Einstein equation, one can get what is the binding energy. This kinetic energy depends on the incident photon energy and the work function of the material. Once you know these parameters, one can derive what is the binding energy, and that gives you the information about the chemical species on the surface. So for this, Sidban got Nobel Prize in 1924 and for his discovery. And the main achievement of this technique is if you have for example, some molecule like this, in which there are for example, carbon is existing in various chemical states or oxidation states, then you have a signature of each of these modes. So this is the formal oxidation state of the atom, and the local chemical physical environment, So this is a very nice technique in knowing what is present on your surface as well as their oxidation states. So with this, we go to the TiO2 and we see that when there is a vacancy present, the spectra changes. For example, this is from the clean surface, but as we start irradiating them with various increasing number of ions per centimeter square, we see the generation of this oxygen vacancy. And this oxygen vacancy, once you knock out oxygen from the surface, it becomes Ti rich in titanium. And once it becomes rich in titanium, titanium nanodots can be produced. So the electrons from here, oxygen gets out, and the electrons from here get transferred to the titanium. So titanium becomes positively charged, and this nanostructures are generated. So this is the process in which the nanostructures are generated on the surface. And these vacancies are also important because the electrons, once you excite the electron that comes out in the conduction band gets captured by these vacancies, because these are like titanium 3+. So once the electron gets captured by them, the recombination also reduces. So this also controls the recombination of the surface. And so in two ways, making of nanostructure and controlling of recombination increases this absorption. So this is the photo absorption as a function of wavelength. How much light is getting absorbed by the material. So if you see, the black curve is the one which was by the clean sample. But as the fluency is increased, or as the number of ions striking the surface is increased, we see that the absorption is increasing in the UV range as well as visible range. So there is a higher absorption in the UV and visible range. And this is due to the formation of nanostructures, presence of oxygen vacancy, as well as reduced recombination. So band gap tailoring has been done. Band gaps have been reduced, but via ion in these studies. Next, we go to the thin films of TiO2, which have been irradiated by ion beams. What we see is a phenomena of also some resistive switching. So in this case, TiO2 thin films, these are nearly 80 nanometer thick films, which were irradiated by 50 keV Ti ions. And what we see is the nanostructures form, but these nanostructures are mixed anatase and butyl. And we see a phase transformation from anatase to butyl forms of titanium oxide. And we also see the resistive switching phenomena. So if we look at the XRD, you see that in the as deposited film, The anatase phase, this feature in the XRD is due to anatase, and this feature in XRD is due to rutile. We see that the anatase and rutile are nearly in similar composition. But as the number of ions increase in the system, in the thin films, the rutile takes over. Here is the weight fraction of rutile, and here is the area of rutile versus area of anatase. In both the cases, you see that the ratio of rutile takes over beyond this fluence, which is about 10 to the power 13. So there is a phase transition happening. But more interesting is if one looks at the size of anatase in this peak, one can use a formula called Scherer formula to get what is the size of anatase zones in these films. And one sees that although in the beginning, around it was big, but as ion implantation takes place, these are small nanostructures remain, but the big ones are missing. And the idea that the big ones are missing is because the big ones have joined together and formed butyl. So although R is the more stable phase, thermodynamically more stable phase, when the surface energy of A is lower. So when the anatase is small, it is stable. But as it becomes big, it gets converted to butyl. It is thermodynamically less stable. So there is a competition between growth of A and transformation into R. And role of oxygen vacancies is also very important. They create the space for this phase transition to take place. These are some TEM images. This is the clean sample in which you see TiO2 film, which is deposited on this gold, nickel, and silicon. And this is the high resolution image where you are seeing the anatase nanoparticle. White is the anatase nanoparticle, whereas black is the butyl nanoparticle. So these are small in the beginning. Butyl is small, anatase is large, but then we see that as ionization increases at 14, anatase is small, butyl becomes larger, and by 115 it's mostly butyl, all the way extending. This is the film extending from here to here, and overall it is the butyl phase which is mostly there. This is the photo absorption and band gap measurements in these TiO2 thin films which have been irradiated. And what we see, although there is not much change in the photo absorption intensity, however, the band gap again shows that the band gap is higher initially and then it decreases. And as we know that the anatase has a slightly higher band gap than butyl. So it is more anatase rich in the beginning, and once the phase transformation, structural phase transformation takes place, the band gap lowers. So we are seeing that the phase transformation is taking place in the films from anatase to butyl at this about 113 dose. Then we have also studied the conductivity measurements in these thin films. And what we do is we have a contact on the top. This is actually coming from the AFM tip. And then current is measured. Voltage is applied between this tip and the film. And this is the gold conducting film. And what we see is something like this, that at very small negative voltages, there is no current. But as the voltage is increased, suddenly we start seeing the current. So this is called the high resistance state when there was no current. Then suddenly when the current starts appearing, we get a low resistance state. So all this is a low resistance state between this voltage and this voltage. And then again, once we go up and then we start decreasing the voltage, again we see the transformation from low resistance state to high resistance state. So this is basically a bistable reversible switching behavior from a high resistance state to low resistance state and then back to high resistance state. This voltage where the HRS to LRS goes, this is called reset. And here where it goes from low resistance to high resistance is called V reset. And the two are of different polarity. One is negative, one is positive. So these oxygen vacancies are very important in producing these kind of LRS, HRS states. So how they do is something like this, that so oxygen vacancies are shown in green and oxygen ions are in yellow. Since we have oxygen vacancies, and if we apply negative potential on the top and negative on the back, gold contact, the vacancies will go towards the cathode and will make channels. These become conducting channels and the current can start percolating between these channels. These are also called conducting filaments. Whereas if it is positive on the top and negative on the bottom, as we were showing, what happens that these two get separated out and these channels get deformed. So this is basically self-assembly of nano channels of oxygen vacancies, which become the conducting path in these films. And this is a bistable reversible switching behavior, HRS and NRS. And also it is bipolar. It is called bipolar because V set and V reset are of opposite polarity. So vacancy states are created by ionization and they introduce the conducting filaments in these thin films. So this, of course, this has many big advantages because this is used in RAM devices, and this is much better than the conventional devices which you need much higher output power. So next we go to the nanobio section. So here we will apply the bottom-up approach of using DNA to make some nano materials and also to use DNA as a sensor. So DNA is a functional material. It is slightly in usual material science, we don't consider DNA as a material, but it is a very interesting material. It can be also used in designing functional materials. It's a programmable scaffold. Of course, it is biocompatible and biodegradable, so it is considered environment friendly. It is environment friendly, and it also has potential for biosensing. So this is a famous XRD figure, which was used to find the structure of DNA. This famous pattern is there. And this photograph called Photo 51 was taken by Rosalind Franklin. Unfortunately, she did not get Nobel Prize because she had passed away by the time Nobel Prize was given in 1962 to Watson, Crick, and Wilkins. So this is the structure of DNA. It is called vDNA, and it was invented in 53, and the prize was given in 62. So what is this model of DNA mean? Important is this, it has a backbone, which is negatively charged. It is the phosphate backbone. And then there are bases in between. There are 4 bases in between, A, T, G, C in the DNA. And A combines with T and G always combines with C with hydrogen bonds. And these are all nitrogen bases, whereas the backbone is phosphate and negatively charged. This diameter is about 1 nanometer, and each base pair is separated by about 0.34 nanometer. So then 10 base pairs is about 3.4 nanometer. So again, this is the same thing, that there is a phosphate backbone and internally connected by the moiety of nitrogen bases, ATGC. This is same base pairing, that G always connects with C via 3 hydrogen bonds, whereas A connects with T with usually 2 hydrogen bonds. This is another interesting phenomenon in the case of DNA. DNA is a double stranded, so the two strands are connected. But depending on the temperature, also if there is some mutation or if there is some defect, this local unzipping of the DNA can take place. The 2 strands can get locally separated. If this denaturing continues, they may even become 2 separate strands, or they become melted. And then they may, again, if the process reverses, they can join together and form this thing. So in our studies, you will see that we will see that some kind of a local unzipping of DNA is taking place, and material gets embedded in between these 2 strands. So what we have studied is the interaction of mercuric ion with these DNA. And why mercuric ion? Because mercury ion is a very toxic to human health. And it is present in contaminated fish and industrial sources. Also, this is a study by World Health Organization regarding the exposure to mercury. And in organic fertilizers and pesticides, when it is present, it moves up via food chain, and we also can get it. So what we have used in these studies is a small circular DNA. And this is a plasmid DNA from this PBR322 from bacteria. And this has about 3000 base pairs. And when we look in atomic force microscopy, what we see is these circular DNA. These are about 600 nanometer in size. And we have interacted these DNA with mercury salt. So this is what happens after we interact, that they do not remain circular, rather they become linear. So the circular plasmid becomes linear after the interaction with mercury concentration. And interestingly, you'll see that something has happened here. And these are the disturbances which has happened in the DNA. Whereas if you see here, these are really like, it looks like they are equally spaced. So these are basically 10 base pairs separated by about 3.4 nanometer. And if you see the high resolution part here, you can clearly see that this is like equidistantly separated. And so DNA is undisturbed in some regions, whereas here and here, actually it has got unzipped, and that will come in the next slides also. And basically these, what we are looking at is mercury nanoparticles which have got deposited here. And how do we know all this, that mercury is here and that some unzipping has taken place? For these, we have used, again, XPS, as we discussed, actually photoelectron spectroscopy, to find out what is happening in these areas. So this is what the DNA looks before its interaction with mercury. And what we are looking in the nitrogen region, that is what is happening to the nitrogen part. This is the amino from the amino group from the DNA. This is the amine group from the DNA, and this is the amine group. But once we interact this with mercury, what happens is we see so many peaks. Of course, these 3 peaks are there, which were related to DNA, but then we see a little peak here and 2 little peaks here. And it turns out that this first one is due to the unpairing of NH2, because the nitrogen bonds are breaking apart. For example, these nitrogen bonds between this base and this base break up. So this leads to this feature. Whereas this and this, as we'll go ahead and see, that this gets contributed by something like these kind of compounds. Thymine is actually supposed to interact with bond with A, whereas what we are seeing that T is interacting with T with mercury in the middle, or T can interact with C with Hg in the middle. And this will be shown by the later slides, we'll show this. But main thing is these nitrogen bases are breaking up and mercury is interacting with these bases. On the other hand, if we look at the phosphorus region, this is from the DNA and this is from the mercury interacted DNA. We see only 2 peaks. Here also for DNA is only 2, and for mercury with DNA is only 2. So unlike nitrogen, we do not see signature of any other peak, which may tell us that mercury is interacting with DNA. So it is not interacting with phosphorus, rather we see mercury is interacting with the nitrogen. So this is some TEM studies also, which show that the DNA is interacting with the mercury, and this is showing the crystallographic structure of the mercury. And from the X-ray diffraction studies also, we see that the mercury lattice constant, from these SAD patterns, we can see that the mercury lattice constant is about 3.4 angstrom. These have been done in liquid nitrogen temperatures. Now, if we look at the DFT calculations, and they have been taken from this reference, that T is supposed to match with always with A, as I mentioned earlier, but in some instances, due to some defect or due to some insertion of some things, this TT DNA duplex can form. This is just a clean DNA, but there is a mismatch. Instead of A and T, there is TT. But when the mercury gets attached to this kind of locations, what they form is THD, T complex. And in this situation, it can make compounds like THDT or CHDT. And these are Hg2 mediated interactions. But one sees that these are very useful in contamination of mercury pollutants from the environment. So these 2 compounds is what give rise to the 2 new peaks in the XPS that we are seeing. This THDT and THDC are coming from these extra compounds. Now, then we have also done transport behavior of DNA. And here, if we look at the DNA alone, then we get this kind of a behavior, which looks like something like semi-metallic behavior. But once we interact it with the mercury, what we see is a rectifying behavior. So this shows us that DNA can be used as a sensor of mercury. And this has its importance, of course, as a decontamination of pollutants from water. So then what we have studied here is that the DNA has unzipped in some regions, and the unzipping regions have included mercury nanoparticles. Mercury is primarily interacting with nitrogen bases, and DNA acts as a sensor of mercury nanoparticles. And this model is basically a DFT result, which is showing that there is a base here, T base here, T base here, and mercury is interacting with both the bases through these interactions. So now we go to the last part of this talk, where we are studying the interaction between the DNA and the TiO2 nanostructures. So this TiO2 surfaces, TiO2 is a very important material, as I mentioned, that it is used in the bioimplants also. And this figure shows the bone cell anchoring itself to the surface of titanium oxide. So this is the titanium oxide surface on which a bone cell is attaching. So the functioning of biosensors depends on the surface properties, its homogeneity, topography, toxicity, absorption and interaction, wetting and compatibility. This important fact, this is also very important, and as we'll show, what we'll see that it is becoming more biocompatible as it is wetting more. So these measurements we will see. So this is a lab on a chip work. This shows that why these surfaces are important. So this is DNA which is interacting with the gold coated surface, and these are single stranded DNA. So this, if you know the exact bases which are sitting on these DNA, and the conjugated DNA is in the material, then it will go and get attached to this specific DNA. And this process is used in the detection of many diseases, and this kind of things are in market for several decades, at least now more than 15 years. So these kind of materials are, these kind of surfaces are very important, but it's important that you have a high density of DNA arrays on such surfaces for monitoring the presence of thousands of genes simultaneously. So this is used for detection of the diseases. But this surface preparation is very important. So, like I said, these all parameters are very important in understanding these surfaces. So for our case, we have studied the TiO2 surfaces, which have been modified to enhance the biocompatibility. And we have studied the DNA attachment on TiO2 surfaces. And for this thing, we have done nano-patterning of TiO2 surfaces using ionization. So these are the ionidated surfaces. This is the clean surface of TiO2 again. And this is after 10-minute irradiation, and this is after 30-minute irradiation. This is what the crystallites on the surface, ionidated surfaces, look like. And this is after we put a DNA layer on these surfaces, respective surfaces. And this is a single monolayer, single DNA monolayer on the surfaces. And if you see that here the diameters look like smaller of the circular DNA, then they look a little bigger, and here they have become fairly big. So this we will discuss further when we go down. But more importantly, they don't look like the usual DNA that we talk about, the cord-like DNA. And the reason is here. So DNA can show variety of morphologies on any surface. DNA can look like this cord type. This is what we usually know as, or it can look like as a single monolayer, or it can look like as a fractal circular structure. And this depends on what is the two parameters. One is what is the DNA concentration, and second, what are the counter ions. Why we need counter ion is because, like we have discussed, that there are vacancies on the TiO2, and these vacancies become also negatively charged. So once you have a negative on the many times on the surface, and your DNA phosphate backbone is negative, so putting one on another, what you need is a positive counter ions. So the concentration of these two decides what kind of a morphology you have on the surface, and what we see is a single monolayer, these kind of structures. So if we plot the diameter on these surfaces. In the case when it is a clean surface, what we see is something like this. But on the irradiated surfaces, the diameter of these DNA increases. And the increasing diameter suggests that the biocompatibility of the surface is increasing. Wetting properties are increasing. So now we look at the XPS. How does the XPS look like? And this is from the without DNA. Right now there is no DNA. It is just this is the clean surface. This is after 10-minute irradiation, and this is after 30-minute irradiation. And if you notice that this is the main TI peak, but this is the vacancy part of the TI peak. This TI3 plus means that the oxygen has gone away from the surface. So it's making these TI3 plus. So these are oxygen vacancies on the TI on the surface. But as soon as we put DNA, this is what it looks like. So this red peaks are due to the DNA coming up. And if you see for the non-irradiated case, also that there is a shift. This is the main peak of the titanium, and there is a shift from the blue peak. Here also there is a shift, but here it is it is sitting more or less on the blue peak. If you see that it is sitting more or less on the blue peak. So basically there was a charge transfer in the initial part. When the DNA goes and sits on the surface, there is a charge transfer. And this represents that the negative charge is getting transferred from the DNA to the surface. And this is a molecular dynamic simulation, which has put adenine on this is adenine base on the TiO2 110. And this is also basically has confirmed our observation that the charge is getting transferred from this base to the TiO2 110 surface. And the nitrogen centers of the bases A give negative charge to the surface, and there is a charge transfer upon DNA conjugation. And this is a adenine base. These are some wetting studies. So this is the oxygen part, what we are looking at now, again with XPS. So this is the main lattice oxygen. This is coming from the TiO2 oxygen part, but then it doesn't have vacancy. But as you see, as we continue to irradiate, the oxygen keeps increasing. This green part is the oxygen vacancy, which increases. And these are the wetting results. So these are the contact angle measurements. And this angle indicates, reduction of this angle indicates that the surface is becoming more hydrophilic. It loves the attached, flattens the water or loves the water, hydrophilic. So once the surface is becoming hydrophilic, then that means the wetting properties are increasing. And that shows that DNA is spreading nicely on these surfaces. And the spreading of DNA on these surfaces is important for all. For example, in our these knee implant, joint implant materials are mostly TiO2, and the better the biocompatibility, more will be the easier will be the attachment with the tissues. Like in the first figure I showed, where the DNA is attaching to the TiO2 surface. I showed you bone cell attached to the TiO2 surface. Same with the DNA. So nanopattern surfaces show better wetting behavior and show enhanced biocompatibility. So in summary, TiO2 nanostructures are produced by ionization, and they show enhanced photoabsorption and band gap tailoring effects. And what we showed that in the visible range, it is becoming better because of these photoabsorption measurements. In the visible range, the band gap tailoring is happening. So once you start absorbing in the visible range, you have help in the visible photocatalysis. And also there is a reduction in the recombination due to the formation of nanostructures. And then we see phase transition from anatase to rutile. And what we see that these anatase particles are nano sizes, but then their sizes decrease as the irradiation increases. And the size is decreasing because the bigger anatase nanostructures are combining to form rutile. And then this resistive switching phenomena is seen, and where the conducting filaments are basically formed due to the vacancies. So these oxygen states, these are the surface states, oxygen states or TI interstitial. which are helpful in doing this resistive switching phenomenon. And in the case of DNA, this is the nanobio part, where we are doing a bottom-up approach in preparing the silver nanoparticles. And silver nanoparticles are getting generated via the mercury interaction, which causes the unzipping of DNA. DNA basically opens up and the Hg gets impregnated in the DNA. And there is a change of electronic structure with the charge transfer from the DNA to the surface. And DNA behaves as a sensor of mercury nanoparticles. And in the case of TiO2 nanostructures, we see that there is an enhanced biocompatibility. Once the surfaces have nanostructures on them, then we can absorb the DNA better. So these are the collaborators I like to thank. These are all my students, most of my students, not all. And so Shanik, of course, Vanraj, Indrani, Subhita, Ashish, Manna is a student who is just finished. And then also Dr. Kanjilal, Dr. Cheney, Sanjeev Srivastava, P. Satyam, Alok Kanjilal, Santosh Chaudhary, and she was my postdoc who was involved in these studies. So thank you.
So I would like to thank Professor Shikha Varma for this nice and very informative talk. So I think now the session is open for discussions and questions. So, okay, I would like to take some questions from YouTube chat first, if Professor Shikha Varma allowed to me.
Yeah, sure, please go ahead.
Okay. So the first question is from Mr. Guru. What he's asking is, if rutile and anatase phase is mixed, what will be the resultant band gap? And
what
how
will be the
it affect
resultant
band gap?
Okay.
And how will it affect the efficiency?
Okay. So, like I said, rutile has a band gap slightly smaller than anatase. And so the band gap of rutile is about 3 and that of anatase is about 3.2. So what we expect that the band gap, depending on the content of anatase and rutile, the band gap will be somewhere in the middle. As it becomes rutile rich, it should be around 3, and as it is when it is anatase rich, it will be about 3.2. So the efficiency of both also will be in between, but TiO2 general shows a good efficiency for photocatalysis, like splitting of water. Of course, the efficiency is not good. It's only 5%. And that was the one I showed you was more for the N-type TiO2, which had some kind of vacancies in that. Oxygen vacancies were present. So in principle, that how the efficiencies change is, of course, it will be a together thing which is measured. Separately in anatase and TiO2 has been measured, but compound will be in between the two efficiencies.
Okay. So another question from YouTube section is from Mr. Gautam Ghosh. So he's asking, how do mercury nanoparticles form from mercury salt precursor, and how much stable are these nanoparticles in DNA?
Okay, so that's a good question. So from here we know that, okay, so it's an acetate what we are using, but when when nitrogen is picking up, it's making a compound. So, and these compounds are expected to be stable. So this is all happening at room temperature, and we are not doing any processing. We are just basically at room temperature, we are interacting the DNA with the mercury and just leave it on the surface for 24 hours and then image them. And even after, if we image it after a couple of weeks, we see the same things that And in the case of XPS, if you see, even the X-ray has been bombarded on these surfaces. And we are seeing this in spite of that. So that shows that these are very stable.
Okay.
Does that answer?
So, yeah. Okay. I think he must be satisfied. So if he wants, he can ask more questions. So I think now let us open the session for question session for Zoom.
I have a
Zoom.
question.
Yeah.
So, Shikha, first of all, a very, very nice talk, and it really spans from physics to the applied to the bio. So, it's really going across the lot of disciplines and applications. So, what I would like to request you to tell, because for the young students who are in the audience who will look at this also offline, it will be very useful, is that how you thought about going from these nanoparticle, I mean, getting from the surface to the titanium nanoparticle studies and then the applications. So some insight that how you, what drove your this journey.
Okay, so of course it depends on the excited students who have a variety of ideas that someone wants to study in the photocatalysis part, and there are then the students who are very excited about biomolecules. So that is the main, I think the main driving force has been in our group, and that's why it's instead of remaining completely focused in one direction, various applications have come into front in our lab. And also the thing is that TiO2 is a very nice semiconductor oxide material, although it has a wide band gap, which is not very good for visible range applications. But as we see that it has a very nice applications and UV range, and they can be modified for variety of applications. TiO2 is routinely used in paints, because if, for example, in regular paints, when you have this photocatalysis, it can remove the odor from the place, it can bring brightness to the paint. So in that case, the TiO2 is a very interesting material, and to see the applications in this range is it has an immense potential. And let's do that. And then the interacting it with biology, of course, TiO2 we all know that is very useful in our implants, shoulder implants, knee implants. To measure how its biocompatibility changes when we make it in nanostructures surfaces or nanostructure range is a interesting topic. So but as I said, our main driving force is students who come up with these ideas that they want to study in these in these zones here. Yeah.
So that's very interesting, and I think this also reinforces one of the points that we like to do research, because you tend to get a chance to do a lot of new things always.
Right. Very nice.
So
Yeah. So yeah, there is advantage in remaining focused in one field also, but then there are also these when you people come up with ideas that we want to try something new, that also is very motivating. Yes. Yeah. Because tendency is to remain work in field in which you are continuing.
Yeah.
So if there are no more questions, so I would like to hand over this session to Professor Vandana Nanad. So I think she can continue from here.
Yeah, so once again, thank you, Shikha, for really, really a nice talk, and it has given the flavor of really going from the basic physics and the to the applied physics, and to the really interfaces like the biology applications, to bringing it out that science ultimately is all same. I also want to thank Dr. Shalik for conducting the lecture and being available here in spite of odd hours, because right now he's not in on the Indian Standard Time. So, and yes, looks like we are already into the Christmas Eve. So the people are getting ready for somewhat a longer break. Maybe students are back in the colleges and are having exams. But I'm sure that a lot of people will watch this video also offline and will benefit from it. So before I take leave, because we'll have one more lecture in this great pandemic and historic year. Next week, we will have a talk by Professor Lahiri on trends in accelerator research super heavy elements to isotopes on nuclear medicine. So we will continue with somewhat biological applications also in the next week. So I hope to see you all. Please pass the word around and do join us next week for the weekly webinar at Saturday at 5 p.m. Bye-bye and thanks a lot again. Thank you.
Thank you, Vandana.
Thank you.
Thank you,
Thank you.
Shalika.
Thank you,
Thank
ma'am.
you.